Welcome to another tutorial. In this video, I'd like to discuss my narrowband processing theory and workflow. This is going to be the start of a multi-video series on my narrowband imaging processing workflow with respect to Photoshop. I just want to say thanks to everybody who has subscribed. It's really helped out my channel and allows me to deliver content like this to you easily. So in this first video, it's going to be theory only. However, I think that it is needed before we jump straight into the Photoshop part, as my workflow may be confusing without this explanation. So without any further ado, let's get started. Okay, so this is going to be the outline, what to expect in this series of slides, this presentation. So what I'm going to start with is AstroEd's theory of astrophotography superposition. So I'm AstroEd, and this is kind of my theory and my workflow and my process. In this first section, we're going to discuss the idea of a signal with respect to astrophotography. We're going to talk about a bit on filters and cameras, important wavelengths and colors, and we're going to cover this idea of superposition, and then how does this superposition apply to astrophotography, and what I actually mean by that. Then we're going to talk about the color hue wheel and color contrast, and then we're going to dive in to my AP narrowband workflow. So let's start out with discussing astrophotography signals. So what is an astrophotography signal? The picture on the right here kind of is a little funny and not accurate whatsoever for what a photon actually is or looks like. However, it kind of gives the gist of the overall ideology or theoretical concepts behind this. So in this particular photon, it's showing some kind of like particle, but also like this wave. And different photons have different wavelengths, and the wavelength is a measurement of the distance from one peak to another peak, and some have long wavelengths, like this one, and some have short wavelengths, or high frequency and low frequency. And it turns out that these different wavelengths, with respect to the visible spectrum, which we'll talk about in just a little bit, these different wavelengths will produce different colors of light. And so the light that you collect, or the data that you collect when you're out doing astrophotography, that data that you collect through your telescope, filters, camera, and into your laptop, that's essentially what I'm talking about when I say signal. And different elements, such as hydrogen, sulfur, and oxygen, emit photons when their atoms are highly energized. So if you have this supermassive star, it's throwing off a lot of UV radiation, all kinds of different radiations. The hydrogen, the sulfur, and the oxygen, they're going to absorb some of that energy, and their electrons are going to jump to higher energy states, meaning their electrons are going to absorb energy, but the electrons don't want to absorb energy because everything wants to kind of be at a state of rest if that's where it was. And so how they go back to that more so state of rest is the electron releases a photon, and it drops an energy level, but then the photon is released. And depending on the element, if it's hydrogen or sulfur or oxygen, it will emit a photon with a different wavelength, and that different wavelength corresponds to a different color of light in the visible spectrum. And so, once again, these different elements emit different wavelength photons, and the different wavelengths correspond to different colors in the visible electromagnetic spectrum. So let's talk a bit on filters. So let's focus over here to the right. So this is the RGG Bayer matrix of filters over pixels of a common passband of an RGB kind of style camera. So right here, you could imagine these gray squares are kind of sensor wells, pixels in a camera, and each one of these red, green, or blue blocks represent an actual filter over that pixel well. So if a blue photon is coming into your camera sensor, and it strikes over one of your blue pixels, well, that is going to be registered in the pixel sensor well as a blue signal. And that filter here, each one of these filters, the red, green, or blue ones, they're quite wide band, meaning if you look over wavelength in the visible spectrum, so let's jump first to what the visible spectrum is. The visible spectrum is the wavelength at which light is transmitted in the visible spectrum with respect from a wavelength of 400 nanometers to 700 nanometers. So 400 is like this purplish, and 700 is your deeper reds, and then everything in between of your colors. And so in, say, a blue filter, it has a passband over these wavelengths. It will allow certain wavelength photons that all kind of have a blue color, shades of blue, to pass in and be registered in the blue channel, and likewise with green, and likewise with red. And you can see that red has a large passband here and lets in a lot of data. And then there's some overlap between the green and the blue channels. And they're really wide band because they let in a wide range of different wavelengths of photons, each within like the range of blues or greens or red. And so this specific plot is a very common plot for like a wideband RGB sensor. And this is for a specific example, just like a Canon 450D. However, my point here is that if you have a one-shot color camera and you have photons striking these sensors, you're going to get a wide passband response. So you're going to let in all colors of wavelength. Now, in narrowband imaging, the point is to isolate very specific wavelengths in order to block out a lot of light pollution, etc. And so you can do that multiple ways. One way is you can use a one-shot color camera and put a multi-band narrowband filter over your camera sensor, and you can accomplish this. Or you can have a monochrome camera, which basically eliminates all these red, green, and blue filters and just leaves you with a bunch of sensor wells. And whatever filter you put over that, that light will pass through and register in every sensor well. So that's the advantage of monochrome, is you can register a lot more light in more sensors rather than in a one-shot color camera. But there's different benefits, and one is time. If you have a lot of time to do monochrome, that's fine. If you don't, maybe one-shot color is better for you. So the point here is that a standard RGB camera sensor, a one-shot color sensor, is going to let in a wide pass band for each red, green, and blue channel. Now, if you put, say, a Triad Ultra filter, which I have, or individual filters if you're doing monochrome for different signals, you're going to have a very narrow bandwidth of wavelengths it can cover. So it's going to cover very few wavelengths, and that wavelength's going to correspond to the elements we were talking about, like hydrogen, oxygen, sulfur, and hydrogen alpha. And so those different wavelengths for hydrogen or oxygen or sulfur correspond to different colors. And so you can isolate them, and then what that does is it, of course, blocks out a ton of light pollution, and it also greatly maximizes the amount of detail that passes through to your sensor of the actual target you're trying to image. So these are some important wavelengths and colors. So if we look at hydrogen beta, it has a wavelength of 486.1 nanometers. And I use this nifty calculator. I'll have to put the link in the description. But you put in the wavelength and it outputs what color that is on the visible spectrum exactly. And so this happens to map to cyan. Oxygen 3 is like a blue-green color that comes out. Hydrogen alpha is like an orange-red. And then sulfur 2 is a deep red. And if you notice the wavelengths here, oxygen is 500.7 nanometers, but then hydrogen alpha and sulfur 2, they're pretty close. They do have some separation, of course, in wavelength, but they're relatively close to each other, as you can see on this chart here, and as well as hydrogen beta and oxygen 3. But this is kind of the natural color of those elements. And here are some RGB values as well as the HSL values, hue, saturation, and luminance values. And you can actually convert between these. If you have the RGB value, you can convert it using calculators online. Once again, maybe I'll throw in a link that can do that, so that if you know the color you want, you can convert it to an HSL value. And that's actually handy in Photoshop, and we'll see that later when we get into that. But next, what I want to go over before we get into my workflow, or how I'm actually, the theory behind my workflow, it's based upon this simple idea of superposition. So if we look at a plot of sinusoid waveforms, they can actually mix with other waveforms. And then they can add together at different points. And that doesn't mean your original wave went away. It just means that things have been added or subtracted to it. etc. And so a better way to understand this at a more fundamental level is consider the number 10. 10 you could rewrite as equal to 5 plus 5, or 10 is equal to 7 plus 3, and so on and so forth. But let's consider if I add 5 to my number 10, well, I'll get 15. And I can add any number to my number 10, or I can subtract any number, or multiply, divide. All these change the value ultimately of 10, but it can still be represented by an equation that still contains my number 10 that's being modified. So an example, if I have some signal and that's equal to 4 times 10 divided by 2 plus 5, well, that's the same as just 4 halves times 10 plus 5, or 4 halves is 2 times 10 is 20 plus 5 is 25, but my 10 is still in there. So why should we care about any of this idea of superposition? Well, let's think of it from an astrophotography perspective. Say I have a nebula that I want to image, and it's emitting photons, and photons have wavelengths, and it's a signal that's traveling from deep outer space, and we're trying to collect it. Well, that signal that's emitted is a pretty pure signal. We'll consider it a pure signal, the signal that we are interested in and want. But what happens if we think about what an astrophotography signal contains? Well, it contains star data, nebula data, photons of different colors in the nebula and stars, and then it also contains this component of noise. So what happens is this pure signal, it arrives here at planet Earth, and it goes through our atmosphere, and there's atmospheric turbulence that adds random noise. There's light pollution that adds noise, and then there's noise in our electronics, our cameras, cables, and laptops. And so if you think of this signal, and then it goes through all those series of noise and light pollution, it's really messy and has this noise component added onto it. However, this signal, original signal, is still in here. And what we like to do in astrophotography is we like to take this messy signal and process it, image process it, to try to get as clean of a signal as we can recovered from that original data. And so I like to think of my AP signal as an equation. Well, it's equal to some star data plus nebula data plus noise. So we know that a lot of noise, like from light pollution, well, a narrowband filter takes care of that. And then if we stack many sub-exposures, that also lowers the noise from atmospheric turbulence as well as additional light pollution. And so we can really minimize a lot of those terms. However, we can't get rid of all of the noise in our electronics and so forth. We just can't stack an infinite amount of sub-exposures to drive our noise completely as low as possible. And in addition to all this, we don't want to do image processing on the stars the same way we do image processing on the nebula. And because of this, we want to separate the signal. And the separation of the signal is this idea of superposition in astrophotography. So let us separate each part of our astrophotography signal and treat each part uniquely to what it needs while reducing the noise. So this gets me to AstroEd's rule of AP superposition. So narrowband superposition in AP, let's take our AP signal again, but now let's think of it in terms of our narrowband data. So our AP signal, well, it's a function of stars and nebulas, right? We have stars and a nebula data in it. This goes the same with galaxies. You're going to have galaxies. Maybe you're not doing narrowband, it's a broadband signal, but you still have photons from nebulosity and gases within the galaxy and stars. So either way, our AP signal is composed of stars and some form of nebula data. And that can be represented with respect to narrowband imaging as some HA signal, some sulfur-2 signal, some oxygen-3 signal, some H-beta signal, and noise. So this signal, of course, can be taken with a monochrome camera and individual filters, say on a filter wheel, and you can take each one of these. So naturally, monochrome filter wheel imaging kind of starts doing this superposition idea where it separates out each signal and you have to recombine them later on in post. But if you have a one-shot color camera and you have a narrowband, multiband filter, and what you can do is you can separate out in post-processing each of these signals because the HA signal is coming in on the red channel. Same with the sulfur, and the oxygen 3 signal is coming on in the green, and some of the blue is also getting in. The oxygen is getting into the blue signal, but H beta is in the blue, and some of the H beta is actually in the O3. But you can separate them out in red, green, and blue in a one-shot color camera, and you can do that in Photoshop. And so, once again, the red channel contains the S2 and HA combined. The green channel contains the oxygen 3, and the blue channel contains the hydrogen beta for the most part. There is some overlap in the O3 and the hydrogen beta, but it still produces unique data in each channel. And so, what this leads me to is the following. Each part of the AP signal needs to be treated separately and according to its unique needs. And most importantly, it needs to be recombined with the most accuracy possible while reducing noise. So this sentence right here forms the basis of my AP workflow theory. So this idea is how I came up with my theory on how I process images. It's the basis, it's the ground, it's the foundation behind my workflow theory. And it's not just mine. This idea is incorporated in all narrowband image processing. By no means is it unique, but maybe the perspective I'm looking at it or how I'm describing it to you may open up some ideas of what's going on, or at least how I'm approaching this with respect to integrating my data into Photoshop and processing it there. All right, so the following images I'm about to show, they're extracted out of the red, green, and blue channels from the original RGB stretched stack using Photoshop. So if you haven't watched my previous tutorial videos and you're wondering how I stretch my data, do operations on my data, I have a 3-part series that covers these ideas. How I stretch my data is using this arcsine hyperbolic stretching in Photoshop. And so this is my data. So I get my one-shot color data, all my subs, and I stack it in Deep Sky Stacker, and out comes an image, and then I stretch it using the arcsine hyperbolic stretching technique, and this is what I get for my Pelican data. And this is the RGB combined data. And so if I then go into Photoshop and I look at the red channel, this is what I'll see in my red channel. And my red channel, once again, this is my hydrogen alpha and my sulfur 2 data, because that's what registers in my red channel. And you can see there's a great amount of detail within the HA signal, just really, really beautiful details. Just quite fascinating how these narrowband filters really extract lots and lots of detail. But there's a difference between my data. So if I go from my red channel to my blue channel, which is oxygen, you see there's a difference. So I'm going to flip back between them. There's a difference in the data. The hydrogen alpha really lets through lots of detail. And the oxygen data, well, it's only showing me responses of oxygen. So the signal is slightly lower in oxygen, because oxygen signals typically are the same with hydrogen beta. But there's still unique data. If I'd really let you guys stare here with me for a while between the two images with the fine-tooth comb, you'd notice that there's differences in the actual detail between the channels. And the same if I flip to hydrogen beta, the blue channel in Photoshop. And so these 3 channels represent my narrowband data. So that's the data after we'd extract it that we'd be starting to operate on. Now, color mapping is important, and I want to talk about colors for a little bit first before we go into my workflow ultimately. But color mapping is important with respect to color contrast, simply because color contrast maximizes the appearance of your details, and it makes the most breathtaking, detailed images possible. So here's my arcsine hyperbolic stretched, and then here's when I process the 3 channels and recombine them. You can really see where the difference in the data starts to come in. So I want to tell you guys right now, I don't sit here with a paintbrush in Photoshop or like a masking and mask in different colors. I don't do that. I let the data speak for itself. I recombine the data in a way that all this detail is where it should be. I'm not painting in the detail or the color. This is truly from color combinations and color mapping, which I want to show you all in this multi-video series. So let's continue to talk about the color wheel and color contrast for a second. So this is the color wheel. It's on a circle. This basically like this annular ring. And you have yellow to start with, and then you go around orange, red, purple, blue, and green. Now, there's 12 different shades of these colors on this color wheel, and what we say is it's 12 hues. So hue is a specific term for color, and the color wheel here shows 12 of them. And the primary colors are equally separated spatially, or they're diametrically opposed. So for yellow, if you have the yellow primary color, it has a complementary color of purple. And the same with blue has a complementary color of orange, and red has a complementary color of green. And it turns out that the max color contrast is between these complementary colors. So red and green have the most color contrast. Same with blue and orange, and yellow and purple. And so using different colors for different data causes an awesome color contrast to form, and it just pops out details even more. I can't emphasize how much color contrast can enhance an image. And to kind of speak to this a little more, on the color wheel, there's different ways you can do complementary color mixing. So one's the straight primary and complementary color, like for this example, red and green. But then you can also do split complementary. So if you have 3 different, say, signals like we do, right? We have a red channel, a green channel, a blue channel. Well, we can map them to different colors that have maximum color contrast. And you can do this in different ways. You can do a triadic that has equal number of spacings between each of the colors you're using. Or you can do the split complementary, where 2 of the colors, they're still separated by another color, but they kind of maximize a contrast to this opposite color with respect to this opposite color. So the Hubble palette, it maps sulfur 2 to red, HA to green, and O3 to blue. And it actually turns out that this is a split complementary contrast. And so this all maximizes color contrast. And as you know, sulfur 2 and hydrogen alpha, they're both red, and so they're hard to distinguish as true colors. So if you really want to see, well, what's the hydrogen alpha data compared to the sulfur 2 data, or what's the hydrogen alpha data compared to the O3 or the hydrogen beta, the best way to show the differences in these elements in your image are to use some form of complementary color contrasting. So this is the specific split complementary color contrast that I usually use. I use kind of an in-between orangish red color combined with kind of a deeper blue to a lighter blue color, and then kind of this cyanish turquoises to green color in my image processing. Sometimes I change this up and I go more towards red. And it all depends, and it depends on how I think the image might look better, or if one split complementary color will look better than another. But this is my basic technique, and I typically don't like greens too much in narrowband images. It's just a personal preference, so I usually try to eliminate green as much as possible and go for a different image color that this split complementary color gives, just because I find it a little bit more pleasing to me in the results. Just personal preference, and you can explore this as an option when you're doing your own narrowband processing. So this gets us to the final content of this series of slides, this introduction to my narrowband imaging process. And this is my overall narrowband AP workflow theory. This is what I use, this is what I go to, and this is how it starts. I use the arcsine hyperbolic stretch to preserve data optimally. And once again, you can find my tutorial on that. I have a separate video all on this. And then I separate out each channel. The red, green, and blue are respectively S2 and HA, O3, and hydrogen beta. And then I use the monochrome executable of StarNet++. There's two. There's the RGB one for RGB images, and then there's a monochrome one. I use the monochrome executable of StarNet++ on each of my channel data because they're monochrome images. They're just black and white images. And it turns out that star removal is even better in a monochrome image than it is in RGB. So you even get a better star removal when you separate out channels. And so I use this monochrome executable of the StarNet++ on each channel to extract the stars so that I get a starless image of my red, green, and blue channels in monochrome. And then from the total RGB stretched image, so the very first one, the stacked RGB image, I also remove the stars using StarNet++, but I use the RGB executable. And what this does is from the stretched RGB data and the starless RGB data, I can form a stars-only image. And so I also already have a tutorial on this that you can reference in my image processing tutorial on StarNet++. I go through a process of how I do this. And then what I do is I will perform slight noise reduction on each starless channel image. And so like I was saying, each channel is kind of unique. And so you should do noise reduction uniquely on each channel. Overall, noise reduction on the image you can do if it's fitting. But this way I find brings a much more subtlety and a very nice result in terms of noise reduction in the overall image when you do it on each individual monochrome image. And then what I do is I'll map each of my 3 channels using a split complementary color set, like I've described previous to this, and I recombine the starless narrowband data in Photoshop. So this is the point in my narrowband workflow that I consider is my super secret weapon, and I've been hesitant to release for a long time, but I feel like that's silly, and it's time to supply what I've learned. I think I'm at a point where I've kind of refined it enough that I can release it to everybody. And so this recombining of the different channels is where the really juice of this series is going to be, the real importance and the real kind of details of how to do it. And it's really elegant. It's a really elegant solution. It's not like the color mapping tool that you can use where you kind of select a region, you try to isolate a region, and then you map that whole region to blue. It's not like that. This really uses an elegant method that I figured out. I didn't find this anywhere. One day I was sitting thinking, how can I combine my data better? And it just came to me. And so I'm going to share that. That may be a separate video all alone when we get to that point, depending on how long and how much content there is to deliver. And then through that process, as I'm doing this recombine process, I'm always doing level adjustments as needed while maximizing details, contrast, brightness through like Photoshop's camera raw filter. And then at the very end, once I'm satisfied, I recombine the stars from the stars only image that I formed from my RGB images. And that's my narrowband AP workflow theory. This is my whole foundation and basis to how I came to producing my narrowband images. So next video, we're going to implement it in Photoshop. We're going to start through this narrowband workflow, and we're going to work through it in an example. And I hope you enjoy this series, and I'll be seeing you guys next time with another tutorial video. So once again, thanks for watching, thanks for subscribing, and if you like this video, go ahead and give it a like. Thanks guys, and I'll talk to you next time.